FlexWatts, a power and workload-aware hybrid power delivery network for energy-efficient microprocessors. The speaker will be Jawad Haj-Yahya. Jawad worked for 13 years at Intel in the Processors Architecture Group. Jawad's awards and honors include the Intel Achievement Award, IIAA, the highest award at Intel. 3 years ago, Jawad decided to join Academy and worked as research scientist at NTU and A-Star in Singapore. There, he led the architecture of 2 projects on cybersecurity and AI accelerator. And 1 year ago, Jawad joined the Safari Research Group at ETH Zurich and is leading several projects on energy efficiency and hardware security. So, Jawad.
Thanks for the introduction. My name is Jawad Haj-Yahya and I will present FlexWatts. In recent years, there is a hot debate in industry and academia on power delivery networks. PDN issues are becoming even worse as process technology scales down. So first, I will give a high-level overview of my talk. Client processors typically use one of 3 commonly used power delivery network architectures: motherboard voltage regulators, integrated voltage regulators, and low drop output voltage regulators. The energy efficiency of each of these PDNs varies with the processor power and workloads. Our goal is to provide high energy efficiency and high performance PDN architecture by leveraging the advantages of each one of these 3 PDNs across the processor's wide range of power consumption and workloads. So to this end, we propose FlexWatts. FlexWatts is a new hybrid adaptive PDN for client processors that introduces 3 mechanisms. First, a new hybrid voltage regulators that are allocated for processors domains with a wide power consumption range that dynamically switch between 2 modes, IVR mode and LDO mode. And secondly, static allocation of off-chip VRs, which have a high energy efficiency for low and narrow power range for the rest of the domains. And finally, a novel prediction algorithm that switches the hybrid PDN to the mode that is most beneficial based on power consumption and workload characteristics. We evaluate FlexWatts using our new architectural PDN spot. And FlexWatts improves the average power for spec CPU 2006 and 3D Mark workloads by 22 and 25% respectively for 4-watt thermal design power system. And FlexWatts reduces the average power consumption of video playback workloads by 11% across all tested TDPs. I will give a brief overview of client processor PDN. So the power delivery network is the electrical system that provides supply voltage to the processor domains. A PDN consists of a power supply, voltage regulators, network of interconnections, and decoupling capacitors and power gates. There are 3 different commonly used PDNs. These PDNs normally use switching voltage regulators and or low drop output voltage regulators. An SVR can be placed into the motherboard, which is called MBVR, or integrated on chip, which is known as IVR. The PDN perform differently based on the processor power and workload characteristics. For example, MBVR and LDO PDNs are more energy efficient at low thermal design power and light workloads compared to IVR, while IVR PDN is more energy efficient at high TDP and heavy workloads than LDO and MBVR. And MBVR is more energy efficient than LDO and graphics workloads. We conclude that a single PDN architecture cannot provide high energy efficiency across a wide power consumption range and wide variety of workloads. So our goal is to provide a PDN architecture that provides high energy efficiency across a wide range of power consumption and variety of workloads. To this end, we proposed a hybrid and adaptive PDN that utilizes the advantages of each one of the 3 commonly used PDNs by dynamically adapting the hybrid PDN based on power consumption, and workload characteristics. So we propose FlexWatts. FlexWatts is the first hybrid PDN to use two types of on-chip voltage regulators, IVR and LDO, to leverage the advantage of both PDNs. FlexWatts efficiently chooses the processor PDN based on power consumption and workload characteristics. We evaluate FlexWatts using our new open source PDN spot model. FlexWatts improves the performance and of CPU and graphics workloads by up to 22 and 25% respectively for 4-watt thermal design power system. And FlexWatts reduces the average power consumption of battery life workloads by 11% across all tested TDPs. We show that FlexWatts is an efficient approach to maintain high efficiency and high performance in metrics of interest in client processors across a wide spectrum of power consumption and workloads with minimal overhead. So thanks for your attention. I will be happy to take questions.
Thank you. So please let us know your questions. So I have one question. I was wondering if you could describe the firmware architecture and what sort of features you consider in your predictive model.
Yeah, so basically, let me show some backup slide. 1 second. So here you can see the description of the algorithm that basically predict which mode is better among the two modes, the IVR mode and the LDO mode, to work with. So basically, the firmware is like in power management, there is multiple algorithms, and most of the algorithms are using tables which are stored inside the firmware. So basically, our algorithm also stores tables for the end-to-end efficiency of the IVR and the LDO. And the parameters that we see in this slide, which is the TDP, and we have also the application ratio and the workload type and the power state. All of them are inputs to other algorithms. So they are already exist in modern processor firmware. So basically the firmware will be using these parameters to decide when to switch between the two modes. And basically the algorithm can be also combined with existing algorithm. For example, if you have the DVFS algorithm, which is switch between multiple frequencies. So once you decide, for example, to go to turbo boost algorithm, which requires DVFS, so then our prediction algorithm can be triggered and evaluate which PDN mode is better to work with. Then we can switch to the correct mode or to the most beneficial mode. And along that, once we resume the execution, we can basically we can resume with the requested frequency of the turbo boost, for example, changing the frequency and the voltage to meet the required frequency of the turbo boost. It's also for other applications, like for example, if you're running video playback, also the same. You can switch along with switching the DVFS, you can switch also the PDN mode.
Thank you. We have a question on chat from Karthik Somanathan.
Yeah.
Does each PDN require a separate power grid? If so, how significant is the area overhead?
Okay, so this question, we were asked this question from one of the reviewers. Basically, no, the answer is no. They have sharing multiple resources. Among them is the power grid. So the overhead is minimal, and we have more details in the paper, but basically we are sharing the decoupling capacitor, we are sharing also the power grid itself, and we are sharing the voltage regulators, which is outside outside the chip.
Thank you.
Mhm.
Any other questions from the audience? So I'll ask one more question. So I notice you're mainly targeting client parts with a lower TDP. I'm just wondering how the efficiency of the different voltage regulators can change as the TDP is increasing, maybe for server or whatever. And also, how would your algorithm potentially change for that?
Yeah, we actually discussed part of this question on the paper. Basically, it's not just about TDP, it's also for applications. So basically, if you have also a server, there is also light loads in the server. So it's correct that the server will have high TDP, but also exists also light workloads there. So the two modes are relevant for the two cases, which is TDP, high TDP, and light or heavy workloads. Regarding evaluation on servers, this will be our next work or future work.
Thanks.
Yeah.
Do we have any other audience questions? Okay, so I'll ask another question.
Yeah.
How, relatively speaking, how fast are the different regulators able to switch modes? And do you find any pathological cases where your predictive model can make wrong decisions frequently and have to switch back?
Yeah, actually, this question is relevant also for normal DVFS. Like if you take a look at DVFS today, and let's talk about Intel processors, for example, the DVFS can take up to 500 microseconds in worst cases. We describe this also in our paper. So there will be also wrong decisions also in the current power management algorithm. So I agree with you that this will happen also in this. So you need to put some hysteresis mechanisms not to switch too much between the modes, which exist in most algorithms today. So there should be some thresholds that need to be tuned post-silicon and carefully like calibrated. Is this answer your question?
Yeah, thank you. But I was just wondering if you had seen any specific cases in any of your analysis where this was often like a pathological case or anything.
Yeah, I will tell you that in some cases, like no switch will happen. For example, if you are talking about low TDP, and so most of the time you will work in LDO mode. And if you are talking about high TDP, which is 50 watt, for example, or above, so most of the cases you will run at IVR mode because the IVR is more efficient. And what you switch only once you have light workloads. So if there is for example, if you take a 50 watt case and once you switch, once you have a combination between light workloads and switching between light and heavy workloads, so then you will have these multiple transactions in the system. But you can it's also correlated in this case to DVFS. So you can also ask the same question what happened in the DVFS because DVFS also takes some time to switch between like voltage and frequency, and this issue is known. So either you stay in one state and sacrifice some power or power or energy in order just to keep these cases at low rate.
Okay, thank you. So I think we're out of time on this talk, so we'll move on to the next talk. Let's thank Jawad, everyone.
Thank you.